to close a bit.
On time. Is everybody?
Yes.
Yeah. Okay. Hello, everybody. So my name is Akhil Kumar. I work in research at Poland. We work on mainly the communication part in Omnidrone. So in the context of Omnidrone, we looked at many different communication technologies to be used for drones, and one of those technologies is millimeter wave. You've probably heard of it in the context of 5G. This new spectrum that's being opened up with two transit data rates that go to gigabits, 10 gigabits per second. And yeah, so I wanted to show you that we actually have some equipment for millimeter wave research in our lab. So we show the setup. So here we have our user, which is normally between each to be drone, recording a video. In this demo, I'm using the video that we made for the Omnidrone project. And then it will need to transmit this to the base station, to the ground station. And so for this, we have this millimeter wave antenna. This is actually an antenna array of 16 antenna elements. And this generates a very directed beamforming pattern, like you can see here from this image. There are 16 beams, and every one of the input ports of the antenna array corresponds to one of the beams. So currently we're using only one beam for this array, and it's going to basically straightforward at the moment. And then on this side, we have the receiving array, where all 16 antenna ports are connected. It basically means that it is a phase of 180 almost kilo two. And go to the base station there where it gets recorded and showing the video like that. Video is disciplinary, meaning that the base station is designed for telecommunications and video part of anything. So yeah, that's why the difference is stuttering, but yeah, you see the data is getting bigger over time. One of the properties of millimeter wave is that it has large fault loss filters, which means that if you send a millimeter wave signal, the energy in the signal gets lost very quickly. That's why we first of all need the highly directed beams to compensate. We can get a more gain in one direction, so we compensate a bit for the fault loss. But yeah, to show this, for example, I can stand in between the signal. Maybe there's actually no signal coming through. While if we look at, for example, a Wi-Fi system, if there was a Wi-Fi and I do Wi-Fi there, that is going to happen. I mean, this is very lossy in that sense. Also, it shows how direct the system is. So we're going to move out of the way. Video continues again. Another way to show this, if I rotate this out of the way, the video obviously stops working. You can see. And then this nice effective sheet of metal. You basically any radio waves impeding on this will just reflect like a mirror. So if you just use a bit of geometry, this one will see from any direction. This one is pointing here. So approximately here, this difficult always. You can see the video. This also shows the problematic property of metal. Any cars or trains or whatever that we use with any traveling means. Yeah, wireless propagation is generally very difficult. What else did I want to say? Yeah, so for in the context of drones again, so this directed beamforming is very much a problem there. Because, yeah, of course, you have to always align towards the user or towards the base station on the ground to get good reception. And if the drone is moving very fast, if it flies behind the building in this context, it will just lose connection. So there we can look into our research and maybe multiple connections at the same time to the drone to different locations on the ground, or we can do smart path tracking to not fly behind obstacles and things like that. So that's where our research is currently going on. What else? Yeah, also millimeter wave specifically. So we're currently using this. This is very fragile, as you can see. It's also because the lab equipment. But in the context of 5G, for example, there's other bands that have been opened up, like 3.5 gigahertz, which is much lower frequency, but that signal is much more robust. You can also do some beamforming there. The antennas are quite smaller than for the 1.8 gigahertz. And yeah, with beamforming there, you can also point towards the user in the air, for example. Yeah, that's actually all. I think that's it what I want to show. Thank you for your attention. Is there any questions?
Is it customized temperature from I or
Excuse me?
how do you configure this setup? It's like
Yeah,
pressures
so
from I or
all software is from NI. The user and the base station are by NI. That's the MIMO framework that we have in our lab. But the millimeter wave equipment is designed in collaboration with Dave Basin. They developed the millimeter wave antenna array, the beamforming, all that circuitry behind it. So that's mainly their skill. But yeah, its main part is NI. But then the millimeter wave part is from Dave in Germany. What's cool about these millimeter wave arrays, if you want to have a look, so the antennas, the actual antennas, if people think of antennas, they think of those sticks on the Wi-Fi router, for example. But here the antennas are these very, very small, yeah, electronic, metal lines at the end. Because yeah, antennas are mainly in the size of the wavelength used. So millimeter wave, yeah, here antennas of a few millimeters. So all that special patterns before. Yeah, so normally these are just antennas in an array. If you want to have those directed beams like in here, you need to do phase shifting between the signals. So there, these RF circuitry comes into play. You basically delay lines. Yeah.
Other questions?
Questions?
Thank you very much.
Yeah, no problem.
And we'll continue our journey.
I will join you now.
Thank you. Yeah, welcome. Welcome to the crowd.
Of the polylating drone, you can see there are two versions of the same drone. So this is a commercial drone, also including the gray extension board. But the processing is done on this front board. It is the mic bits, is it? Sorry, mic bit with a camera 210, and the camera is here. And here, this very small PCB in front is a distance sensor, which is used then in the final phase to approach the flower. And this is a pollinating sticky, but it's not a real sensor. It's pollinated. So my assistant Reese will put the drone on the floor and body to hold the flower. And so all processing is done on the drone. As you can see, this doesn't do anything but charging batteries. So fly to a certain height first, and then it will try to find the flower, and then it will fit in two phases. First, as far as the detector goes, and then with the direct steering visual serving model goes on. So, button. Move it. Now switch it to the model. It knows it has touched it and goes back. We try to let it do a control now, but not too big. So 2 years of research.
Thank you.
Well, yeah, indeed. So the aim is to go to a smaller drone, the nano drone kind of stuff, with a specialized chip, for instance, ROM Magics on it. And then the flowers can be at scale also. So they like cucumber plants flowers or something like that. So we really have to be pollinated, but they are a bit smaller. The nice thing is those small drones are also more agile to fly. So it's more a matter of tuning your PID loops to get it right. That's also now sometimes it's slow because of the PID loops to be tuned. Uh, in the previous demo, we tricked it a bit by walking and found it also more challenging demo. This is the exact demo they did in Dubai 2 weeks ago, and because of Jan Bon will be holding the flower, they took out the angle detection part. I don't know why, because it was much more safe then, and they really didn't want to fix it. So that's why I'm putting the flower now direct towards there. But there is a model which works also which can detect the angle of the flower, and even if it's the backside flower, because that can be the largest flower, which is in the neighborhood, and finds the backside and it flies close enough, and then it goes up the flower, and but the model is trained not with plastic flower, but real flowers, and with 3D models, and it can be able to detect this flower, which is obviously straight up one. Into real.
First of all, this is my chip. I will pass it along if you want to have a close look. This copy, of course. The other one is in there. So shooting board is connected to an FPGA board, communicating with it. And then from there, we're sending it an output to a computer, and the output is there. You feel like having a phone, feel free. Don't worry about breaking it, that one is already broken. So what we can do here is I can select here a few inputs just from the data set. One also is already mentioned the data set. That's the right image, and then in that we expect that we input. And then if I press the go button, but I will hold on for just a moment, we'll start processing these. It takes a few seconds per image. That is mostly because of communication back and forth between the different computers and the post processing. The actual time consumed in the chip, you will see here on the oscilloscope, like a running signal that would give like a pulse. So the duration of that pulse is how long it actually takes the chip to process this. And what do I mean with this? It's like Marianne already mentioned, like the backbone neural network that extracts features from the images, and then those features are compared and post-processed somewhere else. The chip is doing the actual neural network with like 104 gigahertz per input, or also 243 megabits of input and output going in and out of the chip. Quite a lot. It's running at, also already mentioned, at 93% utilization, which means that we can run this network in 63 milliseconds per input. So let's go ahead and do this now. So now it's starting to process things on the chip. So whenever this pulse is over there, the chip is actually busy. And then one by one, we can see here the output coming in. So these are the text sections done from those images. So what's important to note here is that due to our depth first, the actual I/O that we need, the thing that is so limiting to performance, both in energy as well as in latency, we compare it to the I/O that is just the I/O of the network, so that's the bare minimum you can get, right? In the end, you do need to input and your outputs, just temporary data that you want to avoid as much as possible. So the I/O of the actual network is the gray bar here, and the blue bar is what our solution, which is depth first, actually needing. So it's basically the same. While if we weren't doing this depth first approach, we would end up in this wet scenario where we do layer by layer. This is even assuming some best case assumptions, but you can already see it's about 6 times higher. But that would also translate into about a 6 times higher latency because we're limited by this I/O, and also in a much higher energy because right now this I/O is using about half of the energy of the actual processing. So yeah, if you do this 4 times 6, your energy also blows up. So that is why it's that important to do this depth first, and that's why we have this chip that does this depth first processing to stay very big on this I/O, and thus also like the energy consumption. Yeah, that's it. If you want, we can mess around with it. If we're honest, it's just going to look the same with other.
Thanks very much. Questions?
There already a particular application for this chip, or is it all possible?
As in, it's not going to be in any kind of product. That's the question. Yeah, no, that's not going to happen. The application is just as a proof of concept, mostly for this first processing that we can do it with this amount of bandwidth, and then we can process neural networks without the intermediate data. And while this network is only like 4 layers deep, we're at the moment only using 20% of our on-chip feature memory. So make it 5 times deeper, and we still wouldn't have any more I/O externally. Then we would be saving quite a lot more of the I/O and quite a lot more of the energy as well. And so yeah, it's more like something for that. So target applications would be anything that works on like a pixel level. So not classification, because the first thing that classification tries to do is sample down and get more channels. While these pixel processing things, they don't necessarily do that. And if they do that, then they will sample upwards afterwards. In the end, they need the same resolution as the output, right? And so the first is mainly meant for high resolution applications because there you have very, very big feature maps. So it's future visual sense. Yeah. We also had a project with another partner, and they actually were very interested to do this in the backend processing of cameras and smartphones. So these are all computational photography right now. So there it's also very interesting to be able to do this at first because they're not limited by bandwidth and it works more like a pixel level. So I don't know how many of these ideas they will actually put in the project. They will probably never tell me. But these are the kind of.
Yeah, no, I'm pretty ready. So my goal for the demo is to let the drone follow the line. What you can see here is RGB input that the neural network gets. The neural network is trained solely in simulation, where I have a blue line or a red line and white background. And I want to augment my dataset in such a way that it can fly directly in the real world without any real world data collection. My neural network takes as input the RGB input and decodes a map, a semantic map, where it indicates 1 if it's a line and 0 if it's another line. And from these same features, it also decodes a waypoint. And this waypoint is then sent to the PID controller to navigate shortly the drone. All right. Start with the blue line. So as you can see, it can see the blue line, not distracted by the red line. And if I switch here, you will see here that it switched to autonomous now. Right, I overtake. And with another neural network that is trained on red line. This is obviously a more challenging task because the background is full of red lines. And I thought that this red tube would be like a very strict homogeneous red tube. But unfortunately, due to the sun, it actually has some variations in redness, and the background also has some variations in redness. So it's, let's see if it works. Here we start. As you can see on the predictions, it's already a lot less certain, especially when you go further away from the line. And then here we go. Ah! That was not a good start. Try again. Right. So far, so good. Okay. Yeah. Well.
That's the
That's
best.
why there is a net.
Yeah, the best part of drone demos when they crash. Sure. Okay, take
All
care.
right. Yeah.
So I already first explained the camera before the GoPro. So this is the camera. So as you can see, it has 4 sensors. So each of the sensors can be shown here, and each pair, after the pair will be combined into an omnidirectional frame, like this one and this one. So in this high resolution image data, you can create virtual frames. You can zoom in. You can have a look around, or you can just target anywhere you want. So this is also the video data that Sarush will be using in a demo. Also, this demo evaluate for camera post connection network. So we basically had a recording of around 5 minutes or more, and then we annotate it using now. Then we train Postnet. So for each train, Postnet connect the position of this camera and based on the relative position of the other camera. This camera can follow the trajectory and reference for the position. So as you can see, no, the only directional camera is completely towards you. By pressing A, select glass, camera, and zooming on it, then the following. And the nice thing is that also if the camera is not moved, so it's brought by glass, it can still detect the position because there's no object detection for the field detect on the position of that camera. You can also play with the camera, if you put it lower, work or not, it's what to do, and it actually is quite slower. Right. You want to